So these, again, the probability of B failing and C failing, the and is just going to mean multiply. So this is going to be the probability of B failing, which I might write as not B, multiplied by the probability of C failing, which would be the probability of not C. What is the probability of B failing?
Like that?
That's the probability of it working. So what's the probability of failing? Point to expand. What is the probability of C failing? 0.3. This is probability of working, so it fails with probability 0.3. Multiply them together, you're going to get 0.06. So that's the probability that C2 fails, 6%. What's the probability that C2 actually works? 94%. Therefore, now this is a footnote for what's above, so just ignore that. Probability of C2 being reliable is 94%. There, like that. Now this one, you do need A and B or C. So you need the thermometer detected and one of these processes to work. Now there's a 6% chance that both of those processes fail. Therefore, there's a 94% chance that one of them works, which is enough for it to go through either the manual or the automatic and work. So
depend.
it is. I'd say it is. Yeah.
Like B and C have to. A depends on B and C working.
B or C depends on A working.
Parallel.
I prefer to keep it a little on the easier. Sorry, say what you're saying. Okay.
Like A depends on the process depends on B and C working really.
Yeah, you need A needs to work. First, you need to detect it, and then one of these must work. Yeah, that's what I said. If we go to the conditional, I want to keep it as easy as possible here, and is going to be multiply. Simple as that. Okay. So what we have is altogether the answer, the system reliability, probability of the system, the reliability of the system is the probability of the first component working and the second component working. Multiply them together. Probability that the first component works we found is it's given in the question 0.9, and we found that the probability that the second component works is 0.94. And we get an answer of 0.846. So most 85% of the time when the temperature goes critical, this system works. Now obviously different things you can do here. If you get a better thermometer, that will make a little help, but actually improving these systems will be far more effective. Parallel things, if you've two good parallel, a backup to a good thing, it's very small chance that it fails.
Would not be better, A is your single point of failure, so that would not be better that A be the best.
That's what you would think, and that would actually be correct, yeah. So actually what I was saying wasn't quite, I was saying, oh, don't worry about that, make this better. But actually, yeah, you're right. So already this is better than that, yeah. So you need a better thermometer. What you really should have is two thermometers. That would work really well. Two thermometers at 0.9 will work 99% of the time. So two thermometers would make this way better. Okay. Now we'll go back and look at the previous question, page 95, where now most of them you're given the diagram. Sometimes it might ask you to make a fairly straightforward diagram. So in this one, a system consists of 5 identical components, but they're soon to be independent, connected in parallel. Each have a reliability of a number between 0 and 1. We're not saying what A actually is. Express the reliability of the system in terms of A. So the block diagram is 5 in parallel. and each has a reliability of some number between 0 and 1. So I don't really have a, I mean, 5 pilots.
5 what?
Pilots. I don't know when you'd have, I suppose very serious situations you might have 4 backups. Very, 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 very serious. Okay, so the only way that this can fail, so finding the way that it works is difficult because you can have this works, work, fail, work, you know, it's horrible. So it's way easier just calculate what's the probability of it failing. How can this fail? Everything fails. So the probability of the system, the probability of the system failing, probability of the system failing.
We can just say not S there as well, like.
Not not S. Yeah, not S is probably better. I just noticed I've loaded this stuff written, but I think some of the, like you see it on the next page, that does make it harder for some people. This isn't actually hard. Like, well, this calculation isn't hard, and you'll see over the next page if you write it all out. Next hard. Not S would be a little bit better, I think. Yeah, but S failing. So here you need probability. I'd say fail, and fail, and fail 5 times. The ands are going to be multiplied, so you've got probability of fail multiplied by probability of fail 5 times. That's what those dots mean. The reliability is A. What's the probability of failure? Slow down a sec there.
Say it again.
So the reliability of one of these numbers, probably that one of them works. No. Slow down a sec. So the probability of one of these working is A. A isn't given to us though. So if the probability of it working is A, what's the probability of it failing?
5 minus.
A minus 5.
1.5. You're making it way harder. Probability of rain is 20%. What's the probability of not rain? 80%. How did you get 80%?
Take the point away
From 1. So if the probability of working is A, what's the probability of not working? 1 minus A. 1 minus A. So this one failing is 1 minus A times 1 minus A times 1 minus A 5 times. What do you call it when you multiply 1 minus A together 5 times?
Power of 5.
Power of 5. So that's the probability of it failing. So what's the probability of it working? This is easy with the numbers, isn't it? So probability of it, the system.
Multiply it out and.
Oh, horrible. Horrible. No.
1 minus.
1 minus that. If it works. So basically all day long, now say the 20%, 80% is easy, but you probably do need to get down to, for some of them later as well, where you'll have the probability of not something and you won't know the probability of it, it'll take a little bit of time. You need to know that the probability of not something happening is 1 minus the probability of it happening. So for example, the probability of this not working, or rather not working, it's very big. So if the probability of it failing is that, probability of succeeding is 1 minus that. That's the same as the probability of not failing. So this would be 1 minus A to the power of 5. Let me, yeah. So then the second question is, determine the value of A, as an algebra problem here, if the overall reliability is 0.96. So determine A if this is equal to 0.96. So you're kind of reverse engineering the thing here. So if you have identical components and you can put them in parallel, the question is, if you say, like you could work this the other way around, you could say how many components do you need in parallel if each of them have a 50% reliability to guarantee that your overall system reliability is 95%, you could solve a similar problem. Now this one, we are told that we have 5, and the question is, in parallel. What must be the reliability? How good must these be such that this whole system reliability is 0.96? So we have to find the reliability, which is this, equal to 0.96. And you have a little equation. Now that is a bit of a sting in the tail. It is a little bit on the tricky side. So this is the overall system reliability. When is that equal to 0.96? As these went, the first part was not too bad. This is harder. This little bit here. So we got a little equation. Solve for A. Okay, so you are supposed to be kind of able to solve these because you either have MATH6038 or an exemption, but I know it's so simple. I don't see too many equations on this paper, but anyway, you want to get A on its own. What's in the way? What's stopping you having A on its own? The 1. How do you get rid of that 1? Or rather subtract it to the other side, yeah? So I have minus 1 minus 8 to the power of 5 equal to 0.96 minus 1, 0.04. What's in the way? What's stopping you having A on its own? How do you get rid of that minus? Multiply by minus 1. Two numbers are equal. Multiply them both by minus 1. They are still equal. What's in the way now? It's not quite a square, but yeah. Power of 5. How do you get rid of the power of 5? Fifth root. Yeah. So that was on the tricky side. You take the fifth root. If it was squared, it'd be the square root. You take the fifth root of both sides. That's a number you can get out of your calculator. And now you've handled this already. Add, take the 1 from both sides, and also multiply by minus 1. So you're going to end up with, if you do it carefully, A is equal to 1 minus the fifth root of 0.04. Should be only approximately equal. 1 minus fifth root of 0.04. Doesn't have to be that good. 4747. So that means if you've got 5 things in parallel that only work half the time, the system reliability is still very high. It's 0.96. Higher than 0.96. So you got some of the, like the calculation that we did on the previous page written in this notation is there. I don't think you really need that. Now the other example on page 97, I'm going to skip that but write it up and send it to you. And I'll put little notes on it as well. Okay, so we're going to jump on to page 99. So we're going to start with this one, the plants growing in a tunnel. 5 plants in the tunnel, 5 plants on trial, as such. Okay? And suppose we have the probabilities for, and again, we're going to assume independent. Here again, they're not, if you think about it, they're not independent, but we're assuming they are. So and means multiply. Okay? And we have probability that a plant grows to maturity is 0.8, probability that a plant dies before that is 0.2. So we have a success is maturity, and we have a probability of success is 0.8. And we're interested now in x, the random variable, how many plants are successful. And we're interested in here, what is the probability that you have 3 plants living, 2 plants dying. And it's... Okay, so what needs to happen? Now we look at an easier thing. Suppose the first 3 live and the second 2 die. So that's 1 lives and 2 lives and 3 lives and 4 dies and 5 dies. We're assuming independence. We're assuming. So the and just means multiply. So the probability of it lives 0.8 by 0.8 by 0.8. Now automatically if the probability of living is 0.8, what's the probability of dying? 0.2. So by 0.2 and by 0.2. So you get 0.8 cubed by 0.2 squared. So the probability that the first 3 live and the second 2 die is about 2%. Now, that wasn't actually the question that we started with, though. The question was any tree. So there's loads of different possibilities. Now, we'll kind of draw some of them up. There's actually 10, so I won't draw them all up, but like, now, say you had the first tree living and the last two dying. You could also have maybe live, die, live, die, live, or maybe die, die, live, 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 etc. So we're asking, you've got 5 plants, what is the probability that 3 of them live? There's lots of different ways that 3 of them live. Live, 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 die, die, live, die, live, die, live, die, die, live, 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 and so on and so forth. Now, it's this way, or 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 this way. Can you have, say, the first 3 living and the second 2 dying and this happening at the same time? No, so the or means plus. So you're going to have this plus probability of this, plus probability of this, plus probability of this. Now the probability of this would be live, die, live, and so they're going to be multiplied. So it's going to be 0.8 by 0.2 by 0.8 by 0.2 by 0.8. 3 0.8s, 2 0.2s multiplied together. It's going to be exactly the same as that. So all of these things have the same probability of happening, about 2%. And the question is how many different ways it can happen, and that's kind of the tricky bit. Now, it's a bit hard to write out all the possibilities. How do you know you've missed one? Well, there's a kind of special button on your calculator. I kind of gone over this. Skipped over this. You've got this 5C3. Okay? What this means is, and you better find that you should look for it. On a lot of calculators, it's behind division. So I think on a Casio it's behind division. NCR, you have it. You're looking for NCR behind division, yeah. You got it? Yeah. Have you got it? Behind the 5. Anyone not that? Behind 5 in the sharp. Behind the division. Behind the 5 in the sharp. Behind the 5 in the sharp. Anyone there? Anyone not there? Okay, so what this number gives you, I'll probably write it up here. 5 choose 3 is number of ways of choosing 3 objects from 5. So if you're in the tapas, you know, if there's 12 different options, you know, I don't know, eat 5, obviously, and say the number of different tapas meals you could, from the 12, choose 5. Now I won't say how you calculate these by hand, I'll just leave that off, so just use the calculator. So everyone should be able to get, so you do press 5, second function, your choose, and then press 3 and press equals, everyone should get 10. Yeah. And you're in any issues with that? So you do 5, second function, then press where it is, so I think you're behind the division. Then press 3, so you 5 choose 3 equals. Everyone here got it? Yeah. Yeah, okay.
What's the trick? Can you explain the 5 rows? The 5 actually rows.
Oh yeah, so what the relevance of, so the number of ways this can happen is from the 5 plants, how many ways can you choose 3 of them to live?
Oh,
that's why.
That's what 3 stands for.
That's what the 3 stands for, okay?
How do you actually type down the calculator?
So, right, the 5. Now you're going to go for your choose, so it's the second function behind your 5, so the second function choose, and now press 3, and now press equals. Okay, so what you have is there's 10 different ways this can happen, this, or this, or this, or this, add them together, you're going to have the 0.02 plus 0.02 plus 0.02 plus 0.02, 10 times, so it's going to be 10 times 0.02 basically. Okay? Now, doing that every time in these problems is going to be very difficult, so we're going to actually get that going in a formula, and that formula is in the back of your notes. It will be on the tables for your exam. So this is the kind of problem we're doing. We'll set it up a little bit better now, but this is the kind of problem we're doing. Okay, so these random variables that are a finite number of trials. These trials we'll talk about in a second. They're called Bernoulli trials. They have two outcomes, success or not success, and you know the probability of success. And what you're interested in then is, so these are the Bernoulli trials, and then your binomial random variable is x is the number of successes in the end trials. So suppose you have a random variable, only two outcomes, success or failure. Now you have to understand success doesn't have to be a good thing, it just means something that you're counting. Look something like this. So for example, T being the flip of a coin, with success defined as a head. Probability of success is a half. T rolling a dice with success defined as a